Hello, I am Petra and I'm a PhD student in the Department of Molecular Theory and Spectroscopy. And today I will show you an example of calculating some magnetic properties using quasi-degenerate perturbation theory in ORCA. So when I say magnetic properties, I have in mind properties of the EPR spin Hamiltonian. So if you have a molecular system that has a total electron spin that is non-zero, it will have an associated magnetic moment, and then it can be studied by electron paramagnetic resonance spectroscopy. And the contents of EPR spectra are often summarized in terms of parameters of the EPR spin Hamiltonian, which contains the main physical interactions that are happening. So the main one would be the Zeeman interaction between the electron spin magnetic moment and the external field, parameterized by the G tensor. Then if you have some nuclei with non-zero spin, you might have hyperfine interactions parameterized by A tensors. And if your total electron spin is greater than 1/2, you might encounter a term that looks like this, formally in the spin Hamiltonian, looks like this coupling of the electron spin with itself. It's called the zero-field splitting term, and it's parameterized by this tensor D. And in this short talk, I will show you an example of calculating this zero-field splitting in a molecule of oxygen. So here I have prepared a molecular orbital diagram that shows the configuration corresponding to the ground state of the oxygen molecule, which is actually a spin triplet. And when you have a spin triplet, then you expect that you have 3 sublevels that are degenerate. But actually there are some small interactions that originate from relativistic treatment that make the 3 sublevels of this triplet split in energy even before you apply the external magnetic field. In oxygen, there is actually one number that can describe this. That's the D parameter that says how much the lower level splits from the upper 2 levels, because the D parameter is greater than 0. And the upper 2 levels remain degenerate because the other E parameter is 0. So that means that the upper 2 levels are degenerate, even though this does not generally have to be the case for integer spin systems. Now, what are the interactions that make this splitting happen? Well, one of them is the dipolar coupling of the electron-spin, that gives rise to this spin-spin coupling contribution to zero-field splitting. Another interaction is the spin-orbit coupling. Spin Hamiltonian parameters in general, so including zero-field splitting, can be calculated in different ways in ORCA. So there is one family of these methods that is based on response theory, where the spin Hamiltonian parameters are identified with derivatives of the electronic energy with respect to some external perturbations. And then the implementation is quite similar to any other analytical derivative property. The other type of calculation that's possible in ORCA is based on quasi-degenerate perturbation theory, where actually you start from some kind of wave function theory calculation that is able to give you an approximate solution for your Born-Oppenheimer molecular Hamiltonian. And not only the ground state, but also some number of excited states. And then these states that you obtained are used by the program to construct this QDPT matrix. So that would be the matrix representation of the Born-Oppenheimer molecular Hamiltonian, plus the perturbing terms, that's the spin-orbit coupling and spin-spin coupling also, potentially. And then this matrix is diagonalized to obtain some states and energies, and these states and their energies are compared with the form that your effective spin Hamiltonian should have by the program, and the spin Hamiltonian parameters are somehow extracted by making this link. So let's look at an example. First at the calculation that's based on response theory. So here I'm showing the operators that contribute. So from the spin-spin coupling, which looks like a dipolar interaction, you get a first order contribution to zero field splitting, and then from the spin orbit coupling you get a second order contribution, which means that the program needs to solve for a response to the spin orbit perturbation, which potentially does not need to concern you that much, but you might be interested in looking at the input. So this is a kind of simple example, and for the oxygen molecule here, after a DFT calculation, I'm saying in the EPR NMR input block that I want the zero field splitting, and I want both the spin-spin and the spin orbit contributions to that. So the output would look like something like this. It will give the zero field splitting tensor, the matrix, eigenvalues, eigenvectors, these D and E over D parameters that you might be interested in comparing with experiment. So you can see here that it's not completely unreasonably off the experiment. At least it has the same sign and everything. And then the program will print the contributions to the total value. In particular, I picked here the spin-spin and spin orbit. And you can see that in this system, oxygen, both of these terms are kind of the same order of magnitude, and that's actually why I picked this system to show you. Now, if you want to do such a calculation using the QDPT, I have an example here also for the same system. Now, I have to start with a note of warning, because the CASSCF calculations require quite a lot more setup from you as the user, and then the DFT calculations and with response theory on top of that. So there is a lot of advice on setting up CASSCF calculations that you can find in this CASSCF tutorial that I really recommend you check out if you don't know it yet. You can find it in the download section of the ORCA forum. And the things that you need to pick are firstly the active space that needs to represent your system well. Here I just started with the MP2 natural orbitals. And second of all, you also, to get your property, you need to ask for some excited states, not only the ground state. And you need to be aware what kind of states can contribute to your property. So in case of zero field splitting, actually not only states with the same spin multiplicity as your ground state, which would be these triplets that I'm asking for, can contribute, but also states that have total electron spin one less or one more can contribute to the property by coupling with the ground state. So that's why I'm also asking for the singlets here, and actually the main contribution comes from an excited singlet state. Then in the rel block, I'm saying I want spin orbit and spin-spin coupling and the zero field splitting tensor. And in the output, I would like to say first the program does the QDPT calculation only including spin orbit coupling and gives you the property. And then it does the QDPT calculation again. And in that case includes both spin orbit and spin-spin coupling and gives you the property again. And again, you can see that the number changed quite a bit. So in this case, both of these terms are important. So now what I would like to say is that the QDPT calculations can be quite nice if your system has some kind of more complicated electronic structure, or if the spin orbit coupling is large, because then the QDPT will be way more reliable than the response theory calculation. And also what is nice is that in the output you also get this printing of contributions from the states to your property. So this would be the contributions to the spin orbit contribution to zero field splitting, and you see that most of it is coming from this one excited singlet route. Okay, and then if you want to make your QDPT calculation more accurate, you are probably also interested in including some dynamical correlation so to make it better than your CASSCF calculation. And probably the more straightforward way to do that and also feasible way is using NFPT2. So in that case, the program will then use the NFPT2 energies for the diagonal of the QDPT matrix. But it's also possible to do QDPT with other ORCA modules. So here is an example input for multi-reference CI, where I'm starting from the same CASSCF calculation as I had before, and I'm using this CASSCF wave function as a reference for CISD. And again, I'm asking for spin-orbit coupling, spin-spin coupling. And I will not show you the output per se, because I just want to highlight that since ORCA 6, the output from all modules that are capable of doing QDPT calculations has been really unified. And now if you ask for it, both the spin-spin and the spin-orbit coupling contributions should be consistently included there, so that you can make quite direct comparisons between results from different modules. Alright, that was everything I wanted to show you today. I would like to thank particularly Dimitrios Manganas, who had a lot to do with programming these QDPT calculations in a consistent way. I would also like to thank Frank Nese, the whole ORCA team, and I would like to wish you lots of fun with the new ORCA version. Thank you.